The next design consideration we'll review is operating temperatures and corrosive environments. Basically, picking the best material for your application. Over-engineering is always an issue that you have to consider. There's no reason to go with the most expensive material if carbon steel will work fine for you. So to that end, we'll review some of the materials and give you a general idea of what to look for when selecting a material. So RotorClip offers carbon steels certified to 3 global specifications. We offer SAE, DIN, and JIS specs. They're the same material, but they are triple spec to meet your global requirements. And on those carbon steel parts, you'll see temperature ranges from negative 100 degrees Fahrenheit to up to 600 degrees Fahrenheit. And in a few slides, we'll discuss how that range shrinks as your loads or your environment changes. For stainless rings, we have 15.7, precipitation hardened 15.7 MO. This has good corrosion resistance, high tensile strength, and it can withstand temperatures up to 900 degrees Fahrenheit for a short period of time. This 900 degrees approaches the temperature where the precipitation hardening occurs during heat treat. Above this temperature, precipitants come out of solution and you'll see a degradation in the performance of your ring. You may even see catastrophic failure of your application. We also offer DIN 1.4122 stainless. Similar temperature ranges, and then I have a note on here. Why are we not using 420 stainless? 420 stainless has a low carbon content, makes it difficult to heat treat. So you often see a lot of failures resulting with questionable heat treat coming out of these parts. Since the DIN 1.4122 and 15.7 perform better, it's just best to avoid 420 altogether. On our stainless steel for flat wire products, we have 302 stainless, 316, and 17.7. 302 has a temperature limit of 400 degrees, same with 316, and 17.7 will get you up to 650 degrees. The key considerations in stainless that gives it the properties that everyone loves are the alloying elements. So there's a bunch other than those listed, but the key alloys that are useful are chromium. Chromium is what makes stainless steel stainless. Chromium forms a surface film of chromium oxide to provide corrosion resistance. This increases scaling resistance at elevated temperatures. The nickel increases ductility. This makes stainless steel easier to form. This also increases high temperature strength and corrosion resistance. This is particularly useful in industrial, marine, and chemical applications. And then finally, molybdenum, which increases corrosion resistance, adds strength at elevated temperatures, and expands the range of passivity for all parts. Moly also counteracts pitting, especially in chloride environments. To round out our standard materials, we're going to talk briefly about beryllium copper and phosphor bronze. These are 2 non-magnetic options that are very good for marine environments, and you'll see performance up to 400 degrees Fahrenheit. So this is a graph that kind of shows what happens at higher temperatures. As the temperature increases, the performance of the ring decreases. So thrust loads are greatly reduced, material strength is reduced, and eventually the parts will fail completely. So if you're pushing the extreme limits of the thrust load of the ring, You usually want to be in the 100-degree Fahrenheit range. You could go 50 degrees below, 50 degrees above. As you start increasing towards the that's 400 degrees, 300 degrees area, you start to lose performance, and then at 600 degrees, complete failure usually. So as you increase temperature, if you have a lower load, it's preferable. Likewise for beryllium copper, you'll see similar performance curves, and same for stainless steel. At the other end of the spectrum, you have low temperatures. So around -100 degrees Fahrenheit is usually what we call out for most rings. And at this level, impact resistance is greatly diminished. Brittleness sets in, and there's a danger of fracture. We have a few options for alternative materials. A286 is a stainless steel designed for high temperatures. It'll reach up to 1,000 degrees Fahrenheit. Inconel X750 is a NACE compliant material. It can be designed for high temperature or NACE compliant depending on the spring temper used. So you can have 700 degrees Fahrenheit for a max and be NACE compliant, or you can be at 1,000 degrees Fahrenheit for your max and not be NACE compliant. Inconel 718 is great for corrosive environments, not NACE compliant, and will withstand temperatures up to 1,300 degrees Fahrenheit. Alloy is NACE compliant, and 800 degrees Fahrenheit is a good maximum for that one. Hastelloy is a great material for corrosive environments, not so great for high temperatures. 316 stainless and Hastelloy are also great products for seawater exposure, whereas Alloy and Inconel are great for hydrogen sulfide environments. We'll touch a bit more on NACE compliance. NACE is an organization, and NACE document MR0175 deals with sulfide stress corrosion cracking. We won't go too in-depth here, but basically sulfide stress corrosion cracking is a progressive failure type that produces cracking at stress levels that are well below the material tensile strength, so decreased ring performance. All materials have a hardness that's NACE compliant, but some are too low to function as springs. For example, PH157MO has a maximum of 30 to 32 HRC max. It's not high enough of a hardness to have proper spring characteristics. On the other end of the spectrum, Inconel X750 gets you up to 50 HRC max while still being NACE compliant. And as a general rule, retaining rings like to be in that 40 to 54 range for hardness. So 50 HRC max is wonderful. Quick overview of our material naming convention. What we'll do is have our series SH, as we talked about earlier. A 1.5 inch ring would be size 150, and then we'd add a material code. So SH-150 SS would be the 15.7 stainless version. Won't go too far in depth on this slide, but if you're rewatching this webinar in the future, just know this is how we call out materials. On some of the alternative alloys, the symbol changes depending on the wire type, so the specific abbreviation isn't listed there. Finishes that we can add to our carbon steel include standard phosphates, phosphate and oil, and a heavy phosphate and oil. After that, we get into the hexavalent chromes, which are not RoHS compliant. Salt spray hours of 48 and 96, and then 480 for heavy zinc dichromate with sealer. And this is not a commonly used finish, so we don't see it too much in the real world. Below that, we have our Z3X finish, which is our trivalent chromate zinc plus sealer. This is a RoHS compliant finish and provides 240 hours to red rust. Below that, we have a couple of color-only options, zinc flash, copper flash, and then our standard oil that gives you shelf life protection. Copper flash and the zinc flash are great for camera systems if you need a visual of whether a part has been installed correctly. And finally, on our spiral type rings, we offer oil dip as our standard for carbon steel. We can offer cadmium and zinc phosphate for the military versions. And then on stainless steel, we can offer vibratory deburring, passivation, and electropolishing as more finished treatments than actual finishes that are put onto a ring.